session, we are going to discuss on introduction to polymers. So, in addition to introduction to polymers, discuss various type of classification for classify based on what we are going to polymers with some of the then at the end of session, students should be able to identify a polymer on the basis of its physical structural characteristics. Explain the different types of between. Let us look at what is polymer. Certainly, first time if you are hearing the word polymer, you may not realize what exactly it is. But when I say plastic, it becomes easier for you to understand what it is because we are using this plastic in day-to-day life, starting from early morning. Cannot imagine the plastic. Just take the example. In the beginning of the day, you take tooth made up of plastic. Pen we write is made of plastic. So the domestic articles that are used in kitchen, many of the items are made from plastic. These plastic chairs, the computer keyboard, the packaging materials, and whatnot. If you take automobile, many of the parts have been replaced. Metal parts have been replaced with plastics. Of course, tough plastics. Similarly, in aerospace industries, many of the parts have been replaced with tough plastic materials and polymeric composites. So it's very difficult to imagine our day-to-day life without plastic. Basically, these plastics are polymers. What is this polymer? We have seen a simple chemical compound like NaCl. It is a simple chemical molecule. When you put into water, it will dissolve. But polymer is not like that. The molecular weight of a simple chemical compound is very small. Polymer is not like that. Molecular weight of this polymer goes in 10,000 to lakhs. So it is a very high molecular weight compound. And if you put into water, it won't dissolve so easily. It takes hours, sometimes days to dissolve in solvent. We can define the polymer, any polymer in generic. A polymer is defined as macromolecule formed by the repeated combination of several simple molecules through covalent bonds. So when we say simple molecules, they are called as monomers. Polymer is defined as a macromolecule, a big molecule, formed by the repeated combination of several simple molecules, that is monomers, through covalent bonds. The molecular weight ranges from 10 to the power 4 to 10 to the power 7. Very huge number it is. So what are the examples that lies in front of us? When we talk about polymers, in day-to-day life, in various applications, we use polyethylene. The carry bags what we use is made up of polyethylene. Several other plastic articles are there where we use polyethylene. We use nylon, nylon ropes you have heard of, polyvinyl chloride, the pipes what we use in our domestic application for transportation of water and other such applications. Polyvinyl chloride. Teflon. Teflon is very common one, very tough plastic, very highly resistant to chemical attacks, very thermally stable material. Teflon, polytetrafluoroethylene. Teflon is nothing but polytetrafluoroethylene. So this polymer we use as a coating material in pans at home. What we use, the PTFE coating is there. Okay. Similarly, Teflon coating is also there on iron boxes where we use for pressing the glass, hot pressing the glass. So uh, Teflon is used as a coating material. That is with respect to domestic application. When you come to industrial application, there are several application for Teflon. For example, it is used in railway bogies as a lubricant material. Bearings, okay, are used. Pads, bearings are used in railway bogies. So many such applications are there for Teflon. Polyester, bakelite. Bakelite is nothing but cross-linked, phenyl formaldehyde polymer. It is bakelite. So that is another polymer. So I can give n number of polymers. If you look at the examples. Okay. We should look at some of the definitions before moving into the actual topic. I use the word monomer. Monomer is a small molecule of low molecular weight, which combine to give a polymer. Okay, which combine to give polymer. Simple example I'll take CH2 double bond CH2. This is ethylene monomer. Ethylene molecular weight 28. Okay. So many number of ethylene monomers when polymerized, it will give CH2, CH2, N times polyethylene. Depending on number of repeating units, this molecular weight varies. Suppose 1,000 N is equal to 1,000. That means 1,000 repeating units are there in the chain. That means it is 28,000. Molecular weight is 28,000. So monomer is a small molecule of low molecular weight, which combine to give a polymer. These are called monomers. Then the process of converting monomers into polymer, it is called polymerization. The process of converting monomer into polymer is called polymerization. So it is a chemical reaction in which monomer is converted into polymer. Okay. We should remember monomer itself can't undergo polymerization, but it will undergo polymerization in presence of a chemical compound, what is called initiator, or the monomer itself should possess a reactive functional group like OH, NaOH, or COOH, or even SH. So these kind of functional groups will lead to the reaction between monomers. Okay. Short chain polymers are called as oligomers, but this is not seldomly used in practices. Usually we use the word polymer, okay, where the molecular weight is obviously very high. Functionality is the another term we need to understand. It is the number of functional groups or bonding sites present in a monomer molecule. Is called functionality of the monomer. For example, I took the simple example of CH2 double bond CH. What is the functionality of this? It has the capability to form bond here as well as here. Okay, these two electrons are released, they combine with another electron and can form bond here as well as here. So it is a bifunctional. Okay, the functionality of this ethylene is 2. Okay, if a monomer has a functional group OH, its functionality is 1. Okay, so it can form one bond here. So this is how the functionality, or the number of functional groups present in the monomers are called as functionality of polymer. Now, degree of polymerization is the number of monomers used is called degree of polymerization. I gave the example of polyethylene. I'll take a simple example of this polyethylene. Again, N I wrote. Okay, N can be 1,000, 2,000, 3,000, 5,000, 10,000, whatever the number. Okay, based on this, its molecular weight is decided. Okay. So this N is called as degree of polymerization. This N is called as degree of polymerization. It is the number of repeating unit present in the polymer molecule, or the number of monomers that are getting repeated in a polymer chain. It is degree of polymerization. Let's take this. I gave this example polyethylene. Ethylene getting converted to polyethylene. Very large number of integer depending on the repeating units. How many times this chain growth has repeated before a polymerization is stopped. So that depends on the time and the initiator concentration and the monomer molecules available. All these factors contribute to the N here. Okay. So what I said, N is depending on the initiator concentration, how much ethylene you have taken, and number of ethylene monomers you have taken. Second, initiator concentration. If the initiator concentration is high, the reaction will proceed fast. Sometimes it may lead to shorter chain rather than a longer chain. Okay. Then another one I told, per initiator concentration I said, monomer concentration I said, and even the pressure during the reaction what we maintain, that also gives whether a short chain is formed or a long chain is formed. That matters. So all these factors contribute to the degree of polymerization. This is one type of polymer. Another type of polymer, where two different monomers are involved. Here, same monomer is getting added up here. Okay, in the first case. Second case, two different monomers. You can see here, this is adipic acid, this is hexamethylene diamine. What it is forming? It is forming a nylon 6,6. Okay, adipic acid, hexamethylene diamine. Two different monomers are reacting to give, of course, n number of adipic acid is taken, n number of hexamethylene amine is taken. So one monomer unit. So combination of adipic acid, one hexamethylene diamine together becomes one repeating unit. This repeating unit repeats several times, okay, n times. Now what is the byproduct in this? Here there is no byproduct in the first case. What I showed here, no byproduct. But here when two different monomers are involved, so OH from here, H from here, they combine, and what we get, water as byproduct. There are some other monomers where while reacting they produce ammonia, they produce water molecule, they produce HCl. Okay, depending on the type of monomers. Okay, so two types of polymers I have shown. Okay, let us look at the classification of polymer based on the origin. Now how they are being produced. Based on that, we classify polymers as natural polymer, semi-synthetic polymer, synthetic polymer. I'll give examples for each in the next slide. Based on thermal response, how these polymers behave with the temperature or heat, they are called as thermoplastic and thermosetting. Mode of formation, whether simple addition is taking place or two different monomers are reacting to yield a product, okay, whether it is condensation reaction. Line of structure, that means if a polymer is a linear, okay, linear like this, or a branched chain polymer, or cross-linked polymer, okay, like this, okay, it may happen like this. It's a cross-linked polymer. So linear polymer, branched polymer, cross-linked polymer. Based on stereoregularity, we can tell. Then application of physical properties. Now, where do we use this material? In what form we are using this material? Okay, based on that, we can classify polymers as rubbers, plastics, fibers. Okay, tacticity. So basically stereochemistry of polymers. Isotactic. Isotactic where the side groups or the functional groups, either they are placed below the carbon-carbon plane, this is carbon-carbon plane, or all these side groups placed above the carbon-carbon plane. That is isotactic. Iso is same, okay, on the same side. Syndiotactic. So syndiotactic, they are one functional group placed below, one above, one below, one above, like this. Atactic, there is no regularity. Side groups doesn't have any regularity in positioning. So based on tacticity, Polymers are classified as isotactic, syndiotactic, atactic. Crystallinity. Based on crystallinity, polymers are classified as amorphous, semi-crystalline, and crystalline. And polarity of polymers determines whether the polymer is polar in nature or non-polar in nature. For example, if a polymer has OH, example polyvinyl alcohol, it is having OH. Okay, it is a polar polymer. Then non-polar polymer example I can give polyethylene. Okay, it doesn't react so easily. Okay, Teflon is a non-polar polymer. This polar polymer I can add another example of nylon, which are commonly used. Okay, then whether a polymer chain has same monomer or different monomers. Same chain is there or different chain is there. Depending on that, homo chain, hetero chain polymers are classified. So like this, we can give several classification for polymers, okay, based on different aspects. Look at the examples for these classifications. I said natural polymer, which are obtained from natural sources like plants and animals. Cellulose, starch, proteins, cotton, silk, wool, glycogen. These are all the naturally obtained materials. These polymers are naturally obtained materials. Okay. Then synthetic polymers are those which are synthesized from simple molecules. I gave the example of polyethylene, CH2, CH2, CH2 double bond CH2 giving rise to CH2 single bond CH2. The chain is growing, CH2, CH2 chain growth shown like this. This is polyethylene, simple. Polyester, Teflon, okay. Then polyvinyl chloride, nylon, polypropylene. Can give good number of examples for synthetic polymers. There is one intermediate, polymer class, what is called a semi-synthetic. For example, cellulose, if you treat with nitric acid, it will become cellulose nitrate, which is a semi-synthetic polymer. Okay. If you treat with, acetyl chloride, it becomes, cellulose acetate. So they are semi-synthetic polymers. That is another class among this. Okay. If you look at the structure, naturally obtained material, cellulose and starch, they have a chain like this. Okay, chain like this. You can look at this cellulose chain, how their chains are grown. Remember, a lot of hydrogen bonds are there. There is a hydrogen bond. There is a hydrogen bond. Lot of hydrogen bonds are there. So which makes the force very strong force between the polymer interactions. See, polymer is not new to us. It is now studied from long time. In 1830s, Charles Goodyear, he succeeded in producing natural rubber through process called as vulcanization. Addition of sulfur into natural rubber to make it a very strong material, it is vulcanization. Later, after 1830s work of this natural rubber or vulcanization, some 40 years later, celluloid was produced. Okay, it's successfully commercialized. If you recall all these photographic films, we use this hard plastic film, okay, which is a product of nitrocellulose. So nitration of cellulose, when you carry out, it is forming nitrocellulose. This is being used as celluloid material. But it was very slow after the celluloid formation. You see, this is in 1970s. Okay, so the next progression made was after 1930s. Okay, so a lot of once the nylon came into picture, further, a lot of polymers started being recognized in industry. Okay. Further getting into these classifications, thermoplastic polymer is said. What is this thermoplastic polymer? Polymer that softens when heated and hardens when cooled. It can be shaped or molded several times. That means this heating and cooling reshaping process can be repeated. So such kind of polymers are called as thermoplastic polymers. Usually these polymers are now linear or maximum branched chain polymers, and they are partly crystalline and partly amorphous. Examples for these polymer include polypropylene, polyethylene, polytetra, fluoroethylene, that is Teflon. Okay, so thermoplastic polymers are the polymers that soften on heating and harden on cooling. Once shaped, they can be reheated, reshaped, and remolded. Okay, this can be, that means a simple word I can say recycling is possible for thermoplastic materials. Okay. Another class is there based on thermal response, thermosetting polymers. These thermosetting polymers also soften on heating, and they can be shaped into any required shape, and once cooled they become rigid network. There is a cross-linking happening within the polymeric molecule. Because of this cross-linking, it is irreversible in nature. You cannot recycle this material. Of course, they are very strong and form very rigid network. They cannot be reshaped once it sets in. Okay. Example for thermosetting polymers include bakelite, epoxy, polyester, nylon. So these are all thermosetting polymers. Now, the third class among these polymer is elastomer. Elastomer, they can stretch and then revert to its original shape. Simple example, I can take a rubber band. You stretch it, apply the force, stretch it. Uh, it will, elongate several times than its original structure, depending on the applied force. If you release the force, again it will go back to its original size. Okay, so that rubber band is an elastomer. So polymers that can stretch and then revert to its original shape upon removal of force, they are called elastomers. They are amorphous in nature. Okay, so crystallinity is lacking in these kind of materials. They have twisted, flexible chain. You just imagine coils, okay, that can straighten out on applying tension, and they can recoil once you release the force. They have low glass transition temperature. I will define this term glass transition temperature in the subsequent classes. Okay, so examples for elastomer include styrene, butadiene rubber, natural rubber, silicone rubber. So you can give such kind of examples: styrene, butadiene rubber, natural rubber, silicone rubber. So such kind of example can be given for elastomers. You can look at the examples of thermoplastics. We have polyethylene, Teflon, plexiglass. This is polymethyl methacrylate, PMMA, polymethyl methacrylate, polyvinyl chloride. They're all coming under thermoplastics. So I said the polymer, these kind of polymers can become soft on heating and hard on cooling, and the process can be repeated several times. These are called as thermoplastics. So recycling is possible. Thermosettings are polymers which undergo chemical changes and cross-linkings on heating, and they become permanently hard, rigid, and infusible on cooling. These are called as thermosetting polymers. What are the examples? We have phenyl formaldehyde resin. In this phenyl formaldehyde, we have two types of resins. So one is Novalac, another one is bakelite. Okay, bakelite is cross-linked one, Novalac is straight chain polymer. So this is this is a bakelite. So cross-linking can happen here. Okay, further chain growth here. Cross-linking between chains are possible. Novalac is a straight chain polymer. So here formaldehyde concentration can be varied, and we can produce Novalac as well as bakelite depending on the formaldehyde concentration. Then we have urea formaldehyde resin, epoxy resin. These are some of the thermosetting polymers. Based on mode of polymerization, how we polymerize, we can classify these polymers as addition polymers and condensation polymers. What are addition polymers? Polymers which are formed by addition of monomers to each other without elimination of byproducts. They are called addition polymers. See, polymers can be of same monomer or different monomers, but simple addition takes place to each other. Okay. So examples include polyvinyl chloride. Okay, you can look at this. This instead of this CH3, if Cl comes, that becomes called polyvinyl chloride. CH2, CH2. This is ethylene. N number, if you take CH2, single bond CH2. This chain growth continues. Okay, this is polyethylene. So instead of one H, if you have Cl, it becomes polyvinyl chloride. This is vinyl chloride, CH2, double bond CH, Cl. This is vinyl chloride, polyvinyl chloride, CH2, CH, Cl. This is polyvinyl chloride. Teflon, all this H2, H, 4H will be replaced by F. CF2, double bond CF2. They give CF2, single bond CF2, chain growth continues. Okay, so this is polytetrafluoroethylene, nothing but Teflon. Polytetrafluoroethylene, nothing but Teflon. Polypropylene is another example. This is a polypropylene. CH2, this is CH2, this is CH2, 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 CH2. The side group is CH3. So instead of one H, if CH3 comes, it is polypropylene. Instead of one H, if replaced with the phenyl group, that is one benzene group, structure, if you put here, it becomes polystyrene. So CH2, double bond CH, C6H5. Okay, this is styrene. So if you polymerize, it will become polystyrene. Okay. Condensation polymer, where step growth polymerization takes place. Uh, Polymers which are formed by intermolecular condensation reaction through functional groups of monomers with continuous elimination of byproducts. As the number of monomers are reacting, those many number of byproducts are getting released. Okay, they are called condensation polymers. For example, nylon, nylon 66 or nylon 6, both are possible. Both comes under condensation polymerization category. Polyesters, they come under condensation polymer. Uh, Phenyl formaldehyde resin, urea formaldehyde, epoxy, all this comes under condensation resin. Okay, so they are all condensation polymers. So examples, one reaction is shown here where terephthalic acid and ethylene glycol. See this skeleton structure, it shows CH2 here, which is not shown here. Usually in chemistry we write like this. Okay, CH2 twice, OH twice, ethylene glycol. So this is terephthalic acid. So what happens? This chain reacts here. Okay, this water gets eliminated. So reaction between this and this happens. COO you can see here, and this chain getting linked to this carbon. Okay, here you can see here the bond formation has happened here. Right, this gets eliminated out as H2O is going out. Bond is formed between COO and CH2. This bond is getting linked. That is formed here. This is a polyester. Okay, terephthalic acid and ethylene glycol. It is forming polyester. Okay. Then another example, let's say this is a polyamide. This is adipic acid where 6 carbons are there. Okay, diaminoxin or hexamethylene diamine, um, which is uh, again 6 carbon molecule. So that is why nylon 6,6 is forming. This 6,6 refers to this is having 6 carbon, this is having 6 carbon. So 6,6 is coming from these two. Okay, so it forms nylon 6,6. Nylon. This is amide bond, amide linkage. Okay, this is ester linkage. Ester, ester linkage. This is amide linkage. Okay, so these are condensation polymers. Now let's look at now one of the mechanism how the polymers are being formed. I said addition polymers are there and then condensation polymers are there. What I'm going to explain the mechanism is addition polymer, free radical addition polymerization. Again, this addition polymerization can be conducted by using free radicals as initiators. And we can use catalysts like Ziegler-Natta catalyst to carry out this polymerization, or you can use you know what is called heat, okay, or radiation. Okay, so that also can be used to start the reaction. One example we will take here, styrene getting polymerized here. This is styrene molecule CH2 double bond CH C6H5. Okay, this is styrene. I will take another simple example after this and explain with ethylene. So first what is happening is the initiator compounds are forming radicals. Okay, this is the initiator compound which is a highly unstable compound. Upon exposure to heat or radiation, they will break up easily into radicals. This free radical attacks the unsaturated double bond of the carbon-carbon chain. Okay, carbon-carbon bond. So this double bond is there. This is highly reactive. This is also prone to reactive. These two electrons will start reacting. So one of the electron will combine with this electron and forms a bond here. Okay, another electron moves out onto this carbon. So as a free radical. Now this has become radical monomer. First, initiator is converted into free radical. This is highly unstable. That will attack the double bond of this monomer, which becomes radical monomer. This has the capacity to attack another monomer. This radical monomer, you can see here, this radical monomer attacks the double bond of the new monomer and forms bond with this. Okay, bond between this carbon and this carbon. Okay, and this another electron goes out here. So now you can see, okay, so CH2 is here, CH2 is here, this is C6H5, okay, this is C6H5, okay, right. Now what happened? The free radical moved here. Again, now that free radical is there on the last carbon here, okay. It can continue, thousands of times together depending on the monomer availability. So initially you need one initiator to attack like this, okay. Remember, in a reactor, a big reactor, thousands of such chain growth will be happening. First, this is the initiation step. This is, radical formation. This is chain. This is chain growth or propagation. So many number of such monomers get attached or linked together to form a long chain. Okay, this chain growth continues. At some point, that growth needs to be stopped. Either you want to restrict the molecular weight, then you can stop, or sometimes impurities from solvents that are present in the reactor will attack this free radical and stabilize this. Further reaction is not possible. Okay. So what kind of termination is that? Termination, we call it as chain termination. So first step is initiation. Second step, chain growth or chain propagation. Third step is chain termination. Chain termination can happen by several times. One is by combination. Simple. Two polymer chains are there. Uh, Let us put it like this: CH2, CH2. Okay, this is radical. I'll put it as R CH2, CH2. Let us say X times. Okay, or I will show here X times and last here. Okay, another chain R CH2, CH2 Y times CH2, CH2 dot free radical. Two different chains are there. So I said in the reactor thousands of such chains will be there. This X and Y varies from chain to chain depending on when it got started, when the reactions, the availability of monomers, all these factors matters. Whether good mixing is there, effective mixing is there in the reactor or not. So depending on that, this chain growth continues. Once sufficient chain growth has happened, uh, sometimes they themselves two chains come together. Nothing, just this carbon, this radical and this radical combines to make a new bond between these two carbons. Okay, here you can see here new bond formation is there. So big polymer chain has formed. I've shown very few repeating units here. Actually, in reality, thousands of such repeating units will be there. Okay. This is one type of chain termination happening by combination. Chain termination by disproportionation. Disproportionation. What happens? There is one chain here. I said, X times Y times repetition is there. One of the H from here gets attacked to this, okay, and stabilize this. Okay, H is, this H has been contributed to this. Now, this free radical is combining with this H dot and forming a bond between these two. New bond has come. This polymer chain is stabilized. Now, there is no free radical available here. It cannot attack the polymer or the monomer, or itself cannot grow further now because now it got stabilized. The one which has given hydrogen, okay, this electron and this electron forms double bond here, and this got stabilized here. Now here there is no free radical. It cannot attack new monomer, or it cannot grow further. So both chains have got stabilized with this disproportionation. Okay, internally the hydrogen is getting transferred, what is called as disproportionation. Similar to this, there is one more mechanism, what is called as chain transfer mechanism. Termination by chain transfer. What exactly they do in this chain transfer is, suppose you just imagine instead of this, there is a impurity molecule or a solvent molecule that is present in the reactor. This H from here attacks this and it will form this kind of chain. Okay, so that is the chain termination by chain transfer. So that is also possible. Okay, these are three ways of stopping polymerization. Okay, so what I will do, I'll take the example of ethylene. I showed what is it, styrene. Now I will take simple example of this. Okay, n times one monomer I have taken. Okay, let us say this is ethylene. This is ethylene. You need initiator. Initiator compound can be represented like this: either heat or radiation. Now this will break up into radicals. I'll take the example of initiator benzoyl peroxide C6H5COO twice. Okay, either heat or radiation, it will lead to formation of 2C6H5COO dot. Further, it can give carbon dioxide can be released and you get 2C6H5. This free radical dot will be on carbon. Okay, so this I can represent as just R. Okay, now let us look at this. R, this is free radical, is highly unstable in nature. This can attack the double bond of this monomer. It forms RCH2 CH2 dot. Always you should write dot on carbon, because the bond formation occurs on carbon, not on hydrogen. Okay. So now this is a radical monomer. This radical monomer, this is now chain growth has initiated. So initiation reaction, this is RCH2 CH2 dot plus new monomer CH2 CH2. It will give another radical monomer like this. Okay, that radical has come here. So what has happened? This electron, one electron from here, they combine to form bond between these two, and this is the bond. Another electron has moved out here. This is that electron. So this is the free radical. So several times such reaction goes, and you will get CH2, CH2. Let us say X number of times this chain growth has grown. Okay, I will write another chain. For the next step, I need to show you the termination reaction. Y times CH2 CH2 dot. Okay, so this is chain growth. This is initiation. Step 1, chain growth or chain propagation. Okay, the next step is termination. I said several types of termination possible. Termination by one by coupling. What happens? I will take these examples: R CH2 CH2 X times X and Y may be same, or it may be different. Don't worry about that number. Okay, it depends on at what time each chain has started the reaction, and how well you are mixing the reactor to provide a new monomer to each growing chain. So that depends on that. CH2 CH2 dot plus this I will write in the reverse direction so that you can understand easier. CH2 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 Y times. Okay, X times Y times. Now this will combine to give one big polymeric chain. R CH2 CH2 X times CH2 CH2. Now the combination, this new bond is forming. Okay, this one electron has formed new bond. CH2 CH2 Y times. Okay, so new polymer, stable polymer. Now further no reactions possible. Okay, this is chain transfer by coupling. Chain transfer by disproportionation. Same two chains I will show here by disproportionation. What is this disproportionate? One of the hydrogen is abstracted and attached to this. Okay, it will form CH3 here, right? And the one which has given out one hydrogen, another electron combines with this, forms double bond here. So I will write here R CH2 CH2 X times. Here one hydrogen has gone. Okay, only CH is there. Now this is formed This is stable now. This is one polymer chain. Another chain which has taken hydrogen becomes CH3 here. This has become stable again. Y times. So two different, polymer chains, that is polyethylene only, ending slightly differently. One has formed double bond and become stable. One has formed CH3 at the end and become stable. But the basic polymer chain is polyethylene only. Okay, this is chain transfer. This is termination by disproportionation. Chain transfer. I will take another example. Chain transfer. I'll consider only this chain, okay, plus let us say this impurity from solvent, okay, is available. What happens? This hydrogen can attack this, okay, to form CH3 there. CH3 plus, sorry, CH3, CH2, 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 Y times R. Okay, so this is termination by chain transfer. What has happened to this? This R dot will be there. Okay, it's again reactive in nature. This can attack new monomer, and this chain growth can continue with a new chain. Okay, because this R dot is there. So this is how we can carry out, show the mechanism for free radical addition polymerization. Free radical addition polymerization. Now look at this condensation polymers. Uh, Condensation polymers are produced by the reaction between two different monomers having reactive functional groups. You can see here this is one reactive functional group with this adipic acid, another reactive functional group with hexamethylene diamine. So here one functional group is there, here one functional group is there. So this is bifunctional monomer, this is bifunctional monomer. Okay, so when you heat these two, what happens? One H from here, one hydrogen from here, they will combine to give H2O. H2O is eliminated from the reaction, and these two will combine to form one monomer of lengthier unit. Now, this has become one monomer. This, when polymerized, another polymer, it can grow from this end, another polymer can grow from this end. So monomers get attached to these ends, polymerization growth takes place. This we are calling it as nylon 6,6, and this 6,6 comes from the 6 carbon in adipic acid, 6 carbon in hexamethylene diamine. Okay. This way condensation polymer. One example I have given. Many such condensation polymers are available in the market. This is nylon 6. Now previous example what I told is nylon 6,6. This is nylon 6. This is obtained from caprolactam, E caprolactam. And now elastomeric caprolactam. Now what happens is this closed ring structure first opens up. Okay, upon hydrolysis it will opens up, and then each of these monomers get repeated several times to yield nylon 6 polymer. Okay, this is nylon 6 polymer, right? Two ways we can conduct the polymerization: chain growth polymerization. What happens in case of addition polymerization is chain growth. In case of condensation, it is step growth polymerization that is happening. What are the main differences, the features of addition polymerization and condensation polymerization? In monomers, in a case of addition polymerization, you can observe double bonds available in the monomer molecules. So when you polymerize, no byproduct is formed. Okay. Usually, these addition polymers are thermoplastic in nature. That means when they respond to heat, they can recycle themselves. I mean, we can reheat, remold, and reshape the polymers. We can recycle the polymers. These are thermoplastic in nature. Many of these polymers are thermoplastic in nature. Chain growth is at one active center. So that growth once initiated, addition takes place from one end. Okay. Chains are not active after termination. I gave the example, once the reaction is terminated, they are not active, so they don't initiate another reaction. Examples include PVC, polyethylene, polypropylene, Teflon, and such examples. Okay. In case of condensation polymerization, there are reactive functional groups available on the monomer molecules. Reactive functional groups in the monomer molecules. When you polymerize, condensation polymerization, when you carry out, elimination of small molecules like it may be HCl, it may be NH3, or it may be H2O. Such kind of small molecules get eliminated during the reaction. So usually thermosetting polymers are formed by condensation polymers. Okay. Chain growth will be on both the sides. Okay, previous example I showed here, you can see here also it can grow, here also it can grow. Both it is possible. On both the ends, chain growth is possible. No initiator is required. So here in addition polymerization, initiator is required. I said dibenzoyl peroxide, it may be hydrogen peroxide, or persulfates or can be used as initiators. Several initiator molecules can be used depending on the type of polymer. Now, in condensation polymer, no initiator is required. Just two monomers you are reacting each other, and the ends remain active after termination. That means termination, you cannot really terminate. Once the availability of monomer is not there, chain growth will stop, but still that ends will be active. Once again, if you provide the monomers, that can continue. So ends remain active in nature. Examples include bakelite. I said it is a cross-linked polymer of phenyl formaldehyde, bakelite. Nylon, okay, nylon 6,6, nylon 6, then epoxy resin, polyesters, all these come under condensation polymer. So if you look at some of the questions, which is polymer among these first four? Sensibly, these are also having multiple, 5 monomers are there, 10 monomers are there, but we call, the larger molecular weight compound as polymer. This is among these, this is the larger molecular weight compound. So 28 is the molecular weight of the monomer into degree of polymerization is 2000. So this comes to 56,000 molecular weight. So this is a polymer. Okay, this is a polymer. Identify the polymer with high degree of polymerization. It is very simple. The N is 500 here, N is 2000 here. So this is having high degree of polymerization. So this polymer is having higher molecular weight. Rubber can be classified as elastomeric type of polymer. Elastomeric type of polymer. Which type of polymer can be reshaped? Heating repeatedly. Thermoplastic. Okay, they can be reheated, reshaped. Okay. Why the chain ends remain active in the condensation polymers? So we are not using the initiator molecules additionally. The monomers, different monomers themselves are reacting by the presence of the functional groups in their molecular structure. So ends will remain active because of the non-availability of initiators or impurity agents that will bind the ends. Okay, so the chain ends remain active. So in summary, what we have discussed is what are these polymers and how they are significant in our life, day-to-day life. Of course, including the domestic as well as industrial polymers. In many of the fields, polymers are being used. I don't think any field is there without polymers usage. Every field we have polymers being used. Okay, and they are classified based on their origin, thermal response, mode of formation, stereo regularity, mode of reaction that is being carried out. So they are classified. So I gave several examples for this, and also I discussed the mechanism of free radical addition polymerization. By taking the example of one with styrene, another example I took the example of ethylene. So we have discussed these two free radical mechanisms. Okay. So with this, I'll end this session. We will meet in the